Today we are going to discuss liquid crystalline polymers. You know, the polymers are semi-crystalline in nature in solid state, but it is a surprise things to you that how this liquid crystalline polymer exists. You know, liquids are isotropic in nature, and crystalline solids are anisotropic in nature. But when we talk about liquid crystalline polymer, we have to consider the anisotropy behavior of these materials in liquid state. Actually, it tells about some intermediate phase at the boundary between liquid and solid phases. So, that is called liquid crystalline phase. Sometimes it is termed as mesophase. And you can have this concept of liquid crystallinity from the molecular order in due to their positional entropy, orientational entropy, and as well as conformational entropy. So, you can understand well if you take the example of methane. Methane can be solidified by cooling, and if you observe the melting behavior of methane, this positional disordering of methane molecule is exhibited by melting of methane with an attendant contribution to the entropy of fusion. Methane molecule is spherical, spherical in shape. So, when it melts from its solid phase to liquid phase, so only disorder you can find due to the movement of methane molecule, one methane molecule from one location to the other location. So, the disorderedness in the liquid phase arising out of this melting of methane from solid state, it occurs due to the change in position from one location to the other location, because the molecule is spherically symmetrical. Then if you increase one more carbon atom, that means if you take ethane in the homologous series, so ethane molecule, that is CH3, it looks like a rod like this, small rod or small line, you can say. Now, you can have different orientations of this molecule, parallel, or sometimes perpendicular, sometimes angular, in different angle, you can say. Okay. So, along with this positional, that means this molecule can move from this place to another place, as well as it can orient itself either parallel to the original position or perpendicular to the original position, or it can form certain angle to the original position. So, we can have large number of orientations of this molecule when we consider this orientational disordering of this ethane molecule. Then further increasing the number of carbon from ethane to propane to butane to pentane to hexane to heptane, like here one example is given, normal decane containing 10 carbon atoms, that means the molecular size is bigger. Now, here in case of ethane, you see these two methyl groups can rotate along this carbon-carbon bond, that is possible, rotation of this carbon-carbon bond is possible, and we can have infinite number of orientations, infinite number of disordered your stages you can say. So, that is more pronounced in normal decane. So, it is found in this melting of n-decane leading to many more configurations due to rotations about single bonds. So, methane gives only positional disordering, ethane gives positional disordering as well as orientational disordering, and normal decane or beyond methane we can get positional disordering, orientational disordering as well as conformational disordering. So, when a solid is melted, that means when it passes from solid phase to the liquid phase, there is disorder in their molecular arrangement occurs. That means, in the solid phase it may remain in ordered alignment condition, alignment stages. When it is melted, it becomes disordered, that means it becomes amorphous. So, this stage of liquid crystallinity, that means in the liquid phase, this molecule is supposed to be, such type of materials are supposed to form some ordered configuration. All right. Now, if you recall the molecules of ethylene, polyethylene, due to high compactness, it is crystalline polymer, not perfectly 100% crystalline polymer, but it is a semi crystalline polymer. Crystallinity may vary from 30 to 60-70% like that, and sometimes 100% crystal lattice structure can be, crystal lattice can be isolated, crystal can be isolated or can be prepared from polyethylene. Otherwise, many such polymers are semi crystalline in nature. When we pass from polyethylene to other polymers like polyimides, yesterday I was telling you polyimide, say made from pyromellitic dianhydride. When it reacts with phenylene diamine, so on, we can go on increasing on both sides the length of this molecule. Okay. This is the imide linkage, this is the imide linkage, this is the imide linkage, this is the imide ring, this is the benzene ring. So, this molecule you see, it is a double strand polymer containing such ring configurations. Now, this is a rigid type of molecule as compared to say simple carbon skeleton polymer like polyethylene. Right. Now, melting of this type of molecule, if you compare the melting behavior of this type of a polyethylene molecule with that of polyimide molecule, you will find that it remains or prefers to remain in a rod like shape, rod shape. So, by virtue of its molecular structure, by virtue of its double strand structure, it looks like a ladder. You see, these are the steps of the ladder, ladder like structure, it forms rod shape structure. So, molecules having such type of structures prefers to remain in ordered condition even in liquid phase. I mean liquid phase, I mean in molten state or in solution. You can put this polymer in a solvent, you can get a solution. So, that is in that solution it can remain in a rod shaped configuration or ordered configuration, or in melt condition also it can maintain its rod shaped configuration. So, we can say such type of situation, we can say that it is a liquid crystalline behavior, liquid crystalline structure of the polymer. You will see when you see the models of these liquid crystalline polymers, you will understand how molecular composites can be prepared from liquid crystalline polymers, how very strong fibers can be prepared from these liquid crystalline polymers. Thus, liquid crystallinity depends on molecular anisotropy and the manner in which the molecules pack. So, it talks about this molecular anisotropy, and by virtue of this configuration it can remain, it can come closer or it can pack with molecules surrounding these molecules in this rod shaped configuration. By virtue of such configuration, we can get two categories of such mesophasic structures in liquid crystalline materials in the liquid phase. One is pneumatic and the other is smectic or cholesteric. Pneumatic actually is characteristic of or gives a material of low viscosity or lower viscosity, which is of interest in polymer processing, whereas smectic shows high viscosity either in solution or in melt condition. So, two major categories of liquid crystalline polymers are pneumatic phases or smectic or cholesteric phases, pneumatic LCs or smectic LCs or cholesteric LCs, liquid crystalline polymers. Now, here this word polymer process, interest to polymer processing, it is meant that whenever we prepare some polymer, we can get either in the form of solid or liquid or in solution, all right. If we get in the form of solid, it may be in the form of powder. So, after isolation of the polymer in the powder form, we have to purify it. After purification, we get a pure polymeric material. So, in order to make a product out of that polymeric powder material, what we have to do? We have to either melt or we have to dissolve in a suitable solvent in order to process, so that we can fabricate a finished product, say fiber or a film or a molded item, whatever it may be. It needs to pass through some processing steps. For that, we have to decrease the viscosity of the polymer by dissolving in a suitable solvent or by melting through heat treatment, all right. That is called processing. Now, if the viscosity of the melt or the solution is very high, then it incurs huge consumption of energy that will add to the cost of the product. So, it is necessary that if the viscosity of the polymer solution or the polymer melt is low enough, so that some product can be fabricated out of that polymer through machineries, the cost of the product, final product will be less. That is necessary, but in all cases it is not possible. Sometimes even if it is expensive, you have to pass through some machineries, even if it is high viscosity, you have to process it and to fabricate the final product. This liquid crystalline polymers can be divided into two large groups: thermotropic liquid crystalline polymer and liotropic liquid crystalline polymer. When thermotropic means this is related to melt state, melt phase. Okay. When liquid crystalline polymers or shows liquid crystallinity in melt condition, we term this polymer as thermotropic liquid crystalline polymer. That may be pneumatic or smectic or cholesteric again. On the contrary, if the polymer shows liquid crystalline behavior in solution phase, we call it liotropic liquid crystalline polymer. So, what we have learned? We have learned categories of classification of this liquid crystalline polymers: so pneumatic, low viscosity; smectic, high viscosity; or cholesteric, high viscosity; or thermotropic or liotropic if it is liquid crystalline in melt condition, it is thermotropic. If it shows liquid crystallinity in solution, it is called liotropic. Thermotropic liquid crystals are further subdivided into anisotropic, which are materials where the liquid crystal phases are formed on both heating and cooling cycles. Okay. Heating and cooling, repeated heating and cooling, we can get this liquid crystalline behavior. Mesotropic materials where the liquid crystals are stable only on supercooling from the isotropic melt. The polymer melt may be isotropic, but due to supercooling it may form some molecular order that is called mesotropic. The mesotropic liquid crystals are further subdivided into smectic meaning soap, pneumatic meaning thread, cholesteric derived from molecules with a chiral center, asymmetric center. All right. These are actually necessary only to develop some concept on liquid crystalline behavior of these polymeric materials. These liquid crystalline polymers are typically composed of materials that are rigid and rod-like, as I mentioned. These are rigid and rod-like. It maintains the rigidity or rod shape configuration even in the liquid phase, either in solution or in melt, with a high length to breadth ratio, means high aspect ratio you can say. Say suppose this molecule, if you consider once again this molecule, you can have a length of this molecule which is related to end distance, means distance between the two ends of this polymer molecule, one isolated polymer molecule, that is called L, and the diameter, that means if you calculate the diameter considering the bond angles and the bond distance, you can get some diameter, that is L by D, that is aspect ratio. Higher the aspect ratio, better will be the polymer for making molecular level composites. You know, in fiber reinforced composites we can get very strong and durable composites provided if we have long fibers with small diameter, so that we can get high interface area. Smaller diameter means the thinner is the fiber means higher is the surface area, which can provide more interface area for contact between the fiber and the matrix, which is necessary for composites. Contact, not only contact, it is not only a physical contact, sometimes it can be physico-chemical contact. There may be some physical anchorage as well as chemical primary bond formation is there, that will be really very strong high performance composite. So, keeping that aspect in mind, if we can design a suitable polymer molecule which shows rigid rod like behavior in liquid phase, say in solution or in melt, that will be very ideal liquid crystalline polymer, and provided again if it can provide low viscosity, so that it helps in processing the product, processing and fabrication of the product. So, these are ideal situations. It should be low viscous, it should be as crystalline as possible, less amorphous as possible, as well as less viscous as possible. The smaller groups that give the materials liquid crystalline behavior are called mesogens. Now, the things are coming gradually one by one. Mesogens, the things of mesogens will be clear. You see, so suppose this is a backbone chain to which substituents are there like this, Sometimes what happens, these substituents or pendant groups helps in molecular ordering. Say you think of linear polypropylene polymer, where methyl group can make its configuration as isotactic or syndiotic or atactic. Atactic is the random configuration which is amorphous in nature, soft weak polymer, whereas isotactic and syndiotic having regular symmetry or regularity in the molecular configuration, that means in the substituent pendant group methyl group, that leads to isotropy or isotacticity or syndioticity. Actually, the sense is like that. Now, these groups or pendant groups or substituents are known as mesogens, or the groups in the backbone chain like this say rings, say imide ring or benzene ring. these can also be called mesogens or mesogens units, which help in getting this mesophase, means liquid crystalline phase. So, the units in a polymer backbone, in a polymer structure, which helps to get molecular order, to get mesophasic system, are known as mesogens. So, here you can consider these as mesogens, here you can consider these as mesogens. You understand? Is it clear? These mesogens are simply portions of the overall polymers that are responsible for forming the anisotropic liquid crystal segments. Such mesogens can be composed of segments from the backbone of the polymer, as I told in this case, segments from the side chain, as I told in this case, all right, or segments from both the backbone and side chains. That means, you can have a polymer where mesogens can be placed along the backbone chain. You can have liquid crystalline polymers where mesogens are placed as pendant groups. You can have polymer where both these backbone mesogens as well as pendant mesogens can contribute to this mesophasic structure configuration, liquid crystalline behavior. Chains are arranged so that the mesogen portions are aligned in one preferred direction, with the ordering occurring in a three-dimensional layered fashion composed of one group of arrangements called Smectic arrangement. Say, suppose you can have a layer, that means in one layer you can have polymer molecules, one ply. Say, think of laminates or composites. How the laminates are made? We take more than one plies and we assemble the plies like this. Say, stacking of playing cards vertically, one over the other, one top of the other. Okay. So, this way we can get layers of such plies. Now, if the molecules present in each layer, if we consider their order in individual layers, then that can alter the liquid crystallinity behavior. Once again I repeat, say, suppose you have a layer of polymer molecules, imaginary layer of polymer molecules, in which you can have molecular alignment along this direction, all right, in one layer. You can have another layer of polymers where molecular alignment may remain like this, just perpendicular, in the perpendicular direction. In another layer you can have molecular arrangement with some angular directions, neither 90 degree nor parallel, say 30 degree or 45 degree like this. So, this way you can have several layers where each layer have different orientation of the polymer molecules. In one layer it is fixed, but such orientations are different from one layer to the other layer. So, that will give you some arrangement that is known as Smectic arrangement. You will see when I will show you some structural model later, it is coming later. Arrangements called Smectic arrangements. Here the lateral forces between the mesogen portions are relatively higher than the lateral forces between the mesogen portions, that is, all the mesogens are arranged in a parallel and lateral order. I mean if you think of this configuration where mesogens are placed like this, you can have another molecule by its side, okay, where you can have arrangement like this. these are mesogens, the small spheres are mesogens. Identical arrangement. Now, this mesogen can interact with this mesogen. This mesogen can interact with this mesogen. This mesogen can interact with this mesogen. That means, there will be intermolecular interactions through these small mesogenic groups. Now, we can have arrangement also like this. Now, we compare the interaction between 1 and 2 and interaction between 2 and 3. Okay. It can so happen that in this case interaction may be higher than this one, provided they are of opposite nature. If these mesogens are of opposite nature, then say positive negative type of thing, by virtue of their polarity, opposite polarity, their interaction, let us say suppose hydrogen bond. In this case 1 and 2, in case of 1 and 2 interaction will be stronger. Considering the same sense, the interaction will be less between 2 and 3, because there is a distance between these mesogenic groups. So, these intermolecular interactions through such mesogenic groups contribute to the liquid crystalline order in liquid phase, crystalline order in liquid phase. Pneumatic liquid crystals offer much less order in comparison to Smectic arrangements. That is why pneumatic LCPs are of lower viscosity than Smectic LCPs. Very simple concept. Since intermolecular forces of interactions between through these small mesogens are less in case of pneumatic. So, pneumatic LCP exhibit lower viscosity than that of Smectic LCP. Clear? Now, you understand why these pneumatics are characterized have characteristics of lower viscosity than that of Smectic one. In pneumatic LC, the directional ordering of the mesogen portions along one axis is retained, but the centers of gravity of the mesogen portions are no longer coupled. There is parallel, but not lateral order. Consider this one. This is pneumatic, this is Smectic. Look at these two models, pneumatic model and Smectic model. Here you see these are mesogens, which brings molecular order leading to liquid crystalline behavior. In this molecule mesogens are placed like this, in this molecule mesogens are placed like this. So, now the distance between this mesogen and this mesogen is quite bigger than this one. So, this mesogen is close to non-mesogenic portion. That is why the interactive force which contributes to the viscosity in the liquid phase, here it is supposed to be less. In fact, it is the case in reality we find that pneumatic materials, pneumatic LCPs are of low viscosity. We compare this one where these molecules are aligned parallel, here also these molecules are aligned parallel, but not the mesogens are aligned parallel. Okay. Here you see all the mesogens are in one line almost. So, they can have interaction between the mesogens, and that can provide more or closer packing, closer interaction stronger will be the material, either in fiber or in film form or in molded form. Thus, the forces between the chains are less in case of pneumatic, resulting in a general greater fluidity for pneumatic LC in comparison with Smectic structures. If mesogens are oriented parallel to one another, but the directions vary from one layer to the another, then the liquid crystalline structure is termed as cholesteric, as I was telling. Suppose this is a plane of polymer molecules, where polymer molecules are aligned in this way, okay, and mesogens are also aligned in this way. Now, a plane beneath this plane may contain again these polymers, where the mesogens, if they are not aligned in the same direction, will get different liquid crystalline behavior. So, if mesogens are oriented parallel to one another, but the directions vary from one layer to the another, the LC structure is termed cholesteric. That means, for multi-layered configuration, we can get this Smectic structure. More common for polymers is the pneumatic one. The Smectic state is rare and has been observed only for thermotropic polymers by melting only. Aromatic polyamides, as I showed there, aromatic polyamides or polyimides. Aromatic polyamide means aramide, it is a Kevlar fiber, which is used for making bulletproof jacket. That means, it has capability of absorbing huge impact without failure. That property comes from their molecular alignment. Where from it comes? Now, this Kevlar fiber, you see this Kevlar, I think you remember the formula of this Kevlar, aromatic polyamide NaHCO. So, it is made from terephthalic acid and phenylenediamine, all right. Am I right? So, here you see, now this nitrogen, the hydrogen is connected to nitrogen. Now, this hydrogen can enter into hydrogen bonding with one oxygen of a neighboring molecule. That means, if the molecules are placed in such a way that one oxygen comes just below this hydrogen of another molecule, so it can set hydrogen bond and the distance is maintained. So, next to this thing it will have say nitrogen over here. So, this way it can set intermolecular hydrogen bond, this way it shows this liquid crystalline characteristics. So, this aromatic polyamides Kevlar or aramide form a pneumatic LC state in concentrated solution in say paracresol or metacresol, or in concentrated sulfuric acid, or in dimethyl acetamide, or in dimethyl formamide. These are the solvents for this aromatic polyamide aramide fiber Kevlar. Now, let us see the architecture of units, that means this mesogenic units used in forming, used in developing or designing these liquid crystalline polymers. So, there are swivel units, crankshaft, swivel crankshaft units, and bent unit. These are all mechanical models. Swivel, crankshaft, bent, they are all mechanical models. Do you have any idea of crankshaft? Have you seen any crankshaft? Circular motion, transforming circular motion to linear motion, that is done by a crankshaft. Or the vice versa, crankshaft. Now, you see how it looks. Crank swivel units, you see this terephthalic acid, this terephthalic acid OH is there. So, this residue from terephthalic acid, this is from hydroxybenzoic acid, this side acid group, this side OH group, hydroxybenzoic acid, this hydroquinone OO and 4,4 biphenol, 4,4 biphenol. Now, if these units are present in a polymer, then they can give liquid crystalline behavior. Why? You see, this is actually at 1,4 linkage, para-para linkage. So, this can provide more molecular symmetry, as you have seen in case of this Kevlar. Here you see para-para linkage, but you can have also linkage like this. This is less symmetric than this one, because this is 2,5 linkage, this is 2,5 linkage, whereas this is 1,4 linkage. So, 1,4 linkage in benzene ring can provide maximum molecular symmetry, linear molecular configuration can be available from 1,4 linkage. So, in both these cases we find, in all these cases we find 1,4 linkage. So, linear molecular structure can be available from this kind of units. These are known as swivel units. So, if these architectural units are incorporated in polymer backbone chain structure, we can get very good liquid crystalline behavior in melt or in solution. Look at crankshaft unit. You see, here is the linkage site, another linkage site is here. So, 2 phenyl rings are fused over here, say naphthalene. So, here it is 2,6 dihydroxynaphthalene, okay, 6 hydroxy 2 naphthalic acid. So, here you see dihydroxy, hydroxy acid, in previous case you saw dicarboxylic acid, hydroxy acid or biphenol or hydroquinone. The same thing, you see the properties will be different, the melting point, their solubility, all these properties will radically change if you move from one architecture to the another architecture. In the previous case, you see these were the architectures, but these groups are same, carboxyl groups, dicarboxylic acid, hydroxy acids, hydroquinone or biphenol. Okay. Having the same groups, but with other design, it gives you crankshaft unit. It actually disturbs molecular symmetry, affects molecular symmetry. So, if you have molecules containing that 1,4 linkage, para-para linkage, there you will have maximum symmetry, higher viscosity or higher melting temperature. It is causing certain problems in processing, then you can incorporate in few places such units. So, melting point will be decreased, you will see later. Yes, please.
Sir, maybe Kevlar shows a high mechanical strength, sir, but it will be a poor liquid crystal as far as its pneumatic structure is concerned.
What is the problem?
No, sir, because schematic structures have better liquid crystal properties.
Kevlar is a crystalline polymer. Okay. It forms pneumatic structure. Pneumatic structure. Why? If you critically examine critically try to practice on your notebook. You write the formula of this Kevlar polymer, then you write another molecule, formula of another molecule, try to get this oxygen atom close to this hydrogen. Then in the next unit you will have hydrogen either this side or this side. So, if this oxygen is aligned this way, that is also possible, then you can get more of your liquid crystalline behavior, and that too pneumatic one, because it is not always possible that you will get the orientation of these oxygens, or it will remain, say oxygen will remain this side and hydrogen will remain this side. Do you understand? So, it affects the alignment of the mesogens, alignments of the mesogens parallel to each other, alignments of the mesogen parallel to each other. If such alignment is available, then we can get Smectic structure. If it is not available, we will get pneumatic structure. Do you understand? Because of that reason, because there is some rotational flexibility is available over here. We do not know what configuration, what rotation it will provide in that temperature, that will dictate the extent of pneumatic phase. You understand? So, this is crankshaft unit, then bent rigid unit. Here you see 2 5 positions, again same carboxyl groups, hydroxy acids, and that is resorcinol, this is resorcinol, OH, same group, but where they are linked to the benzene ring, that dictates whether it will give you high melting properties or low melting properties. So, in order to get a liquid crystalline polymer, you have to have a design first, make a molecular design, then you find out the reactants, okay, with such design, then you mix those reactants, then carry out the polymerization, you will get the polymer as per your desire. Now, the same concept will be clarified if you look into this slide. Strategies employed in commercial and experimental liquid crystal copolyesters to reduce the melt temperature, as I was telling you. Now, you see here this is a polyester made from terephthalic acid and say 1,4-dihydroxybenzene. Okay. It forms a polyester. Because of this molecular symmetry, 1,4 linkage, melting point is higher than 600 degrees Celsius, and that too you have to heat this polymer in inert atmosphere, either in nitrogen or helium or argon. Otherwise, if you try to melt this polymer exposed to air, it will degrade, decompose prior to melting. That means, you cannot visualize its melting phenomena. In order to get visualize its melting phenomena, you have to heat this polymer under inert atmosphere, and that is again higher than 600 degrees Celsius. So, you see why here you can get also again the correlations between molecular structure with its property. This melting point is a property. How the melting point is related to its structure, you can understand this thing, and which is again related to molecular order. That means, it will give you more packing, as well as the backbone chain contains rigid phenyl ring. You have seen in case of polystyrene that rigid phenyl ring remains as a pendant group. Here this phenyl group is present along the backbone chain. So, whereas polystyrene melts above say 120 130 degrees Celsius temperature, whereas this polymer melts quite higher than 600 degrees Celsius temperature, and the reason you can understand. Clear? Okay. Then look at this polymer. Now, here this unit, these two units have been kept over here. Now, in order to decrease the melting temperature of this polymer, certain percentage of this unit this is a, what is this unit? This is crankshaft unit, this one, some crankshaft unit is placed over. So, this is 0.5, this is 0.4, this is 0.1. Anyway, this ratio is dictated, that means you have to select these monomers or select these compounds in suitable proportions, so that this quantity will dictate, will regulate the melting temperature, because these two will provide molecular symmetry. That means that will take this molecule towards crystalline structure, whereas this will disturb this crystallinity because of this linkage, crankshaft linkage. So, by due to the inclusion of this 0.4%, only, say its melting temperature decreases from 600 to 400 degree. So, that is at your hand. So, you can regulate that. Here lies the tailorability of such polymers. You can tailor the melting temperature of such polymers by introducing a small quantity of this monomer or this reactant. Further, you see the temperature can be decreased from 400 to 350 if you incorporate this monomer. You see these units are kept, this is also kept, and again little bit of this swivel unit, sorry, bent unit, this bent unit, it actually further reduce this temperature to 350 degree. Okay. Again substitution, this methyl substitution, that can be anywhere, here, that substitution further the same, the first structure, this one, when any of these two two rings are substituted with having methyl substitution, then the temperature has come down from 600 to 400 degree. So, this is again another strategy, either introducing your architectural unit, or you put a substitution, include a substitution, that is further decrease the temperature, melting temperature. When the volume of the substituent is made bigger from methyl to phenyl, it has come down from 400 to 340 degree. Okay. Then spacer units, say flexible units, here you incorporate flexible units, say 4 methylene units, temperature has come down from 600 to 210. So, this shows you can tailor this molecular structure, you can tailor the properties of the polymers by molecular design, and you have the flexibility of polymer synthesis due to the presence of these functional groups. These functional groups will react, but the unit to which these functional groups are attached, they are not reacting, but they are adjusting or controlling or regulating their melting temperature or their solubility also. LCPs with flexible spacers, as I showed, spacers are either regularly distributed, spacers means some unit placed between two rigid units, that is called spacer. If that is flexible, so that will decrease the melting temperature. Say compare polybutylene terephthalate with polyethylene terephthalate. Polyethylene terephthalate and polybutylene terephthalate. In place of ethylene, you have added butylene, that means from in place of 2 methylene units, you have placed 4 methylene units. So, melting temperature comes down, flexibility increases. So, same concept over here. Regular spacers, pneumatic, smectic and cholesteric mesophages occur in many polyester systems involving regularly distributed flexible spacer units. The two main requirements are: the rigid unit must exceed a certain critical length of the spacer. The flexible spacer unit must be less than a certain critical length depending on the structures of both units. These are all self-explanatory. You put your time, you devote your time, I think your concept will be clear. These are the flexible spacer units, CH2, CH2, CH2O, okay, polyethylene glycol like that, or other units PET, HB, hydroxybenzoic acid, etc. This way you can change. What I want to show you, actually the aromatic polyamide structure and the polybenzazoles structure form the bulk of commercial liotropic LCPs, solution phase liquid crystalline polymers, with the aromatic polyamide hydrazide being of interest. In the main, they are spun into fibers, but there has been much study of using polybenzazole molecules in molecular composites. These molecules are dissolved in solvents to make liotropic dopes. Dopes means solution is called a dope. If you put something is a highly high viscous system, it is called dope. Solution of a solute in a solvent is called a dope. Two kinds of solvents may be used. Look at the solvent: concentrated sulfuric acid, or chlorofluoro or methane sulfonic acid, or anhydrous hydrofluoric acid, hydrogen fluoride. You see, very critical solvents, very strong harsh solvents. Aprotic dipolar solvents such as dimethyl acetamide containing 2.5% of a salt to increase the polarity. Actually, these materials, lithium chloride or calcium chloride, they increase the polarity of a solvent. Sometimes if a solvent is unable to dissolve a solute, then you add certain electrolytes there which will increase the polarity of the solvent, and that will easily dissolve the solute. What I want to show, look at here, anisotropic units giving rise to liquid crystal phases. Those anisotropic units which may be present in polymer backbone, that may be rod like shape, helical shapes, or disc type shapes, or plank type shapes. Molecular assembly like this, in helical, rod like, or disc, or planks. So, that gives you liquid crystalline behavior. Now, you see comparison of three liquid crystal phases: pneumatic, smectic, cholesteric, and isotropic. You see, this isotropic means they are the units, they are oriented in random direction, there is no fixed direction, that is why this is isotropic. But when these are arranged like this, they are parallel, but the mesogens are not close to each other in the parallel lines, parallel molecules. So, they are called pneumatic, because the interaction between these mesogen units are less, whereas when they are arranged parallel, mesogens are arranged parallel, it looks like this, it is called smectic. Now, as I told that if you have layer like structures like this, in one layer alignment is in this direction, in another layer alignment is in this direction, in another layer alignment is in this direction. So, this is called cholesteric, and you can consider this kind of cholesteric arrangement as molecular composites. You understand, molecular composites, where there will be some dispersed phase in a dispersion medium, which is continuous phase matrix. All right. So, you can consider this as molecular laminates. So, if we can develop sophisticated conditions of polymer synthesis, we can synthesize molecular laminates with cholesteric liquid crystalline phase structure configuration, and those can provide high performance properties. Types of liquid crystal polymers, again these are mesogens, as I was showing you, side chain liquid crystal polymer, that means liquid crystallinity is contributed by these mesogens attached to side chains, whereas there is no contribution from this main backbone chain. Main chain liquid crystalline, here these mesogens are in the main chain. Okay. Commercially available thermotropic liquid crystalline polymers: Vectra copolyester, Hext, Celanese, Zyder tar polymers, Amoco. You look at these things, structures, these are commercially available. People are using, doing research, developing newer and newer polymer blends using small percentage of such commercial LCPs with say polyethylene, high density polyethylene, or with polyesters, or even polycarbonates. They are taking say 5 to 10% of these LCPs thermotropic liquid crystalline polymers, commercially available liquid crystalline polymers with polyethylene or polycarbonate or polyamides etc., and they are getting much higher level of properties for high performance applications. These are the comparison of properties is written, if you please read. I have already discussed these properties, it is not difficult to understand. These are the properties in tabular form, okay, and look at the applications, area, property and applications, electrical or electronic applications, fiber optic applications, aircraft applications, aerospace applications, as well as industrial applications, medical applications, fiber applications etc., and again this other way these applications are shown over here. So, even for biomedical applications, these liquid crystalline polymers today find major contribution there, and industrial motor components, lamp housings, and you see some muscle actuators also, muscle actuators, artificial muscle actuators, they are made from these liquid crystalline polymers. Okay. Electrical applications, connectors, capacitor bushing, printed circuit boards for fiber optics, for connectors, strength membranes and couplers, and aircrafts, parts of space vehicles, aircraft engine, helicopter, missiles, so and so. Thank you very much.